Welcome and thank you for joining me at my science booth, where I'm going to present to you about a new tool for the investigation of radiative transfer within sea ice. So my name is Christian Katlein. I'm a sea ice physicist at the Alfred Wegener Institute, and on this project I've worked together under the framework of Sentinel-North at the University Laval in Quebec, together with Simon Lambert-Girard from Takovik, Lovro Valcic from Brunsin, a Croatian company building buoys, and my colleagues Philip Anhaus, Marcel Nicolaus, and Mario Hoppmann. So why is it important that we measure light in the Arctic sea ice ecosystem? So first of all, we know that the lightscape under the Arctic ice is significantly changing. So we found that there's thinner ice, there's more melt ponds on top of the ice, and this increases light input into the ocean, but also into the bottom layers of the ecosystem, basically fueling the sea ice associated ecosystem with the common food chain as we know it, from microalgae up to polar bears and down to deep sea sea cucumbers at the sea bottom, for example. So understanding this chain of radiative transfer is very important to judge anything on how the ecosystem is going to be developing. So, for example, the problem is that we know a lot in current climate models about the physical properties, how ice thickness is going to change, how sea ice type is going to change. And by now we have accumulated quite some models and measurements about apparent optical properties, so sea ice albedo and transmittance. And both of those are somehow represented reasonably well in climate model parameterizations. But so far they are not really interlinked. So there is this missing link in between, and this is the inherent optical properties, so the absorption and scattering properties of the sea ice that get linked by a structural optical model to the physical properties, and with those we could compute with a radiative transfer model also the apparent optical properties to really create true feedback loops here for the model. The problem is we know very little on these two parts, so we need novel observation technologies and particularly in ice measurements to learn more about the material properties of sea ice. To do so, we build on the experience of many years of work with thermistor chain buoy data. And what we basically did is we converted a digital temperature chain into a light sensor chain. So the first prototype was developed in 2018 and deployed on the Arctic Ocean cruise from the icebreaker Odin. And the prototype was 2.5 meters long. Now we have it in a 3.5 meter long version. It has 48 or 64 sensors, each 5 centimeters. Here on the top you see a picture of this chain, and these little red dots are what are actually the sensors. These are RGB light sensors, meaning that they are multispectral in characteristics. We have that development costs around 10,000 euros, and the cost of the chain only is about 2,000 euros. So this is all following a low-cost approach to make this technology as accessible as possible. Of course, then data transmission has to be typically handled through Iridium short burst data, like for most other buoys as well. So the sensor is a very small multispectral sensor that is originally a sensor for low-cost electronics for color measurement. And here you can see the spectral sensitivities of the red, the green, and the blue channel. But the interesting thing is also that this also has a clear channel, the black line here, and this follows fairly closely of what the wavelength response of cheaper power sensors. So what we, for example, also have here is that this sensor, because it has a flat surface, already has a pretty good cosine response. It has an infrared filter blocking out longer wavelengths, and thus is really nice for measuring light in the sea ice environment. This is an overview about our first deployment in summer 2018, close to the geographic North Pole from the icebreaker Odin. You see here a typical Ramses spectral radiometer station measuring incoming reflected and transmittance irradiance. But here on the side, this little tripod is holding up the light chain that goes through the entire ice and is looking out at the bottom, allowing us measurement of the light field within the sea ice. This is how such data looks like. Obviously, with the first prototype, we still had some issues here with some mechanical damages to some of the chips on the board. And the color indicates how much light the chain measured. The top part is here, the air compartment, the ice, and the water, and you can nicely measure the vertical profile of light towards the end of the season, and you see how the light is disappearing and it's getting darker towards the end. Overlaying here on the top, you have the measurements from a close-by snow buoy, and you see that as snow thickness is increasing, this light measurement obviously follows because the sensors are slowly stacked with snow. To have a bit closer look here, you see the measured profiles. These are one's on a linear scale, this is on a logarithmic scale. You see nicely, you can see this exponential decay of light through the ice bottom, but you can also see already on the bottom, top and the bottom, some features where light decay is not really following the idealistic exponential decay. To compare the quality of our sensors, we of course used the chance that we had a full hyperspectral station right next to it, so we could compute sea ice transmittance through the hyperspectral station, but also our light chain approach, which is, as I said, at a cost of only 2,000 euros, at least a factor 10 cheaper, or even much more cheaper than the full hyperspectral setup. So also by geometry, we wouldn't expect a very close match here, but you can see it here for the different channels and also in the scatter plot. The match between the two methods is actually pretty amazing. So we can already derive the basic parameters just of sea ice transmittance well from this system. But that's not really what we are after. We are after to look into the ice optical properties. So here we can, for example, derive extinction coefficients from the chain. And this is a vertical cut through the ice. So on the left axis, y-axis, you have the depth in the ice, and the right axis you'd see the extinction coefficient. And you see that within the ice you have a rather continuous extinction coefficient around with values around 1, as we know from literature. But then in the surface layer, this increases much above 10, and also towards the sea ice bottom, where we get more and more photon loss towards the bottom, we get significantly higher extinction coefficients. Now we can also look how these extinction coefficients develop in time and how they are changing over the course of our measurements, and we can clearly see differences here. Now you might wonder, actually, because we have a chain going up and down and the sensors looking sideways, whether this is actually a reasonable measurement. And we of course asked ourselves that the same, and we calculated these profiles for in the discrete ordinate model for normal planar downwelling irradiance, and then also scalar downwelling irradiance, and then also our sideward irradiance. And if you do that, you figure out that actually what you measure with a sideward looking irradiance sensor in a highly scattering medium is almost identical to spherical irradiance. You basically just need to multiply it with a factor of 4 to get to scalar irradiance. So this is very interesting because also for most biological studies you actually want to have scalar irradiance for the correct light levels that are available for algae, and not just planar irradiance as the physicist likes to measure it. So here I want to show you some videos now from the more recent deployments that we have made during the Mosaic campaign. And there you see, for example, here on the left side, this is the deployment that started on the Mosaic main coring site. And what you see here, first of all, you can see temporal changes, but you can also see how the top layer of the ice has a different attenuation characteristics than this ice further down in the ice column. So you see clear differences here between the older ice and the newly grown ice of the new season. What you also see that then, for example, on site L3, where it is solely consisting of first year ice, you see that you have a very consistent attenuation throughout the ice cover, and there's only little things changing within the ice cover. What you now see is that, well, first of all, the surface is changing constantly, but you start also seeing these spikes appearing here in the bottom, and this is actually algae growing on top of the sensor chain. And if you look carefully, you might also see that this average slope, so the extinction in the water, is changing over time. So we can see how this extinction is changing through the ice column and through the water column. And you can see here, for example, in the top, how the ice is melting. Then as we are progressing further down the season, the summer stations failed and we had to continue looking into autumn, and there we got the chance to deploy a station inside a melt pond, and here you can see the refreezing process, how the light field changes in the surface, how the characteristics change, that the slopes inside the ice are slowly changing, and that is a particularly very nice, interesting data set. As you see, of course, already we have this measurement always for 4 channels, so we can look into spectral signatures. And here on the top you have the ratio of the green channel over the red, green, blue integrated channel, and in the bottom the same for the red channel. And maybe it's slightly weak, but you can see that here between mid to end of May you see an intensification of the green color in the water, so that might be either some water or some ice bloom of algae. Later on you clearly see here this green algae growing on the sensor, and what is interesting is that actually at some point these algae start to change color and they get more red rather than green, so either that's a change in species or the physiology of the. One big advantage of these autonomous systems is also that well, you know that Polashten had to leave the flow for quite some time during that spring period due to logistical reasons, and these blue markers really show the gap that is in the main Polashten mosaic data. And you see that all these interesting things of algae growing underneath this sensor and this potential bloom happening was actually while Polashten was gone, and from an ecosystem standpoint it was pretty much done once sampling restarted. And the interesting thing is also that we have here a sudden change in color in the light, and this is related to an event where suddenly the surface turned from snow covered into slightly melt pond covered, even quite early in the season. And this might have caused some flushing, maybe sloughing off some algae in the ice. But these platforms really enable us to look in detail into the biooptical characteristics of CS and the attenuation in CS. So to sum up, this light chain is an easy and low-cost tool for in-ice light measurements. The results are very comparable to traditional setups, just with the advantage that we get multispectral measurements inside the ice, which so far we're not able to. This allows us to improve our understanding of inherent optical properties by feeding these data into radiative transfer models and inferring the optical properties. What we also found was this equivalency of sideward and scalar irradiance, which is very useful to understand the light field in CS. And after all, this spectral resolution also allows us to assess the state of the ecosystem and its development over the season. And if you are more interested in this, you can read our publication that just recently got published in the Cryosphere. And with that, I want to thank you very much for your interest, and if you have any further questions, you're welcome to contact me here on the conference portal and chat with me or make a video date with me so that we can interact and bring this technology further towards the future. Thanks very much.